ladies and gentlemen, and welcome to the Institute of Astronomy, where this morning we are going to hear the public lecture being given by Saul Perlmutter and Brian Schmidt, and we're going to hear all about the exciting discovery of the acceleration of the expansion of the universe. After the lecture, there will be an opportunity for us to take a handful of questions from the audience, and following that, out here there is a tea and coffee reception at which you will be able to meet with the lecturers and also members of their prize-winning team. So do plan to stay behind and do that. The Gruber Prize for Cosmology dates from the year 2000, and since 2001 it has been awarded in conjunction with the International Astronomical Union. I'll read you the citation for this year's prize. The Peter and Patricia Gruber Foundation proudly presents the 2007 Cosmology Prize to Saul Perlmutter and Brian Schmidt, and to the Supernova Cosmology Project and the High-z Supernova Search teams for their discovery that the expansion of the universe is currently accelerating. These observations require the development of new techniques that use supernovae exploding within distant galaxies to measure the precise distances across a large fraction of the observable universe. The discovery of the accelerated expansion has radically changed our perspective of cosmic evolution. The prize was presented yesterday at Trinity College, and there could hardly be a more appropriate venue for this morning's public lecture, because late in 1915, Arthur Eddington, working in the observatories over here, received a copy of Albert Einstein's paper on the general theory of relativity, and Eddington quickly understood that this new theory of gravitation would be of profound importance in understanding the universe. And spectacularly, in 1919, at a total eclipse of the sun, Eddington and his team were able to confirm one of the three predictions of the general theory of relativity. This morning we're in the Hoyle building, which is named for the British astrophysicist and cosmologist Fred Hoyle. And Hoyle was responsible for establishing here in 1967 the Institute of Theoretical Astronomy. The older parts of the Hoyle building date from 1967. Hoyle was associated with the theory of steady-state cosmology, and he was a great passionate defender of his theory, and he was a passionate attacker of the Big Bang theory. So there's a certain irony that we're gathered in Hoyle's building to learn even more about the Big Bang. So, ladies and gentlemen, please welcome our prize winners, Saul and Brian.
That's it, ladies and gentlemen. All right. Hopefully we get back here in a second. There we go.
So today we will be discussing for you the exploding stars and an accelerating cosmos. And I'm Saul Perlmutter from University of California at Berkeley.
And I'm Brian Schmidt from the Australian National University. And we are here today representing our two teams. So I think we're going to have both teams rise up. There's a lot of us here. 51 people in total, almost all of which are here. And we're going to try a tag team. Never has been before attempted between two astronomers talking simultaneously on the same subject. And so we're hoping this goes smoothly, but it's not guaranteed.
Later we're going to on board, Bill. So the questions that began all this work are actually the sorts of philosophical questions that you can imagine people asking from very dawn of time. Questions about whether the universe is infinite, whether it goes on forever in space, and whether it will last forever. What's its fate? What's the fate of the universe? And surprisingly, after thousands of years of philosophizing on such questions, in the 20th century, Einstein's theory of relativity gave us conceptual tools that allowed us to grapple with this in a much more, scientific, precise way. You could start drawing graphs, which we'll be explaining to you in this talk, that would begin to address this kind of question.
At the same time, we had the beginnings of observational cosmology, and I always trace the beginnings of observational cosmology to someone you probably haven't heard of, Vesto Melvin Slipher. And what Vesto Melvin Slipher did is he took the light of galaxies, spread it out into the colors of the spectrum, and was able to look at the fingerprints of atoms. For example, sodium has a color of light which is orange, and what you see in lights around Cambridge, those orange-colored lights, that's because they're full of sodium. Every element has a similar set of fingerprints, and what he went out is he measured the galaxies, and he noticed when he looked at galaxies that their light was stretched a little bit to the red. And he called that, he thought of it being the Doppler shift, so just like sound, when you hear a car driving by you and you hear the pitch of sound stretched or shrunk a little bit, and so the pitch goes higher as an object gets closer to you, and goes lower in pitch as an object is going away from you. Light is the same way. When something emits light coming towards you, it turns a little bluer. When it's going away from you, it is a little redder. And so he went out and measured this for many galaxies, about 50, and what he saw was that almost every single galaxy was moving away from us. And that was a big problem in 1916 because it indicated that we were in some special place, a place where everything was going away from us at fairly rapid speeds of hundreds or even thousands of kilometers per second.
So how could we understand this sort of bizarre, almost paranoia you might start to feel at this stage of why is it that everything is running away from us? And also, is there something about the order of which ones are running away faster that might give us a clue? Well, it turned out that you could try to order these same galaxies by their distance, and the way to get at distance was to use the brightness of these distant objects. So just like if you held a candle or a 100-watt light bulb and someone walked away from you across the room, you could tell how far away they were by how bright the light bulb or candle appeared. You can use the brightness of these distant galaxies to reflect the distances of these objects that are all moving away from us. Now, this is what Edwin Hubble did back in 1929, and he was in fact using the brightest stars within these galaxies, which he was assuming were all about the same brightness, that you would reach the maximum brightness in a given galaxy. And he found a very interesting effect, which was that the larger the redshift of the galaxy, in other words, the faster it's trying to get away from us, the further it is, the fainter it is. And this is exactly the hallmark of what we would see if the universe is expanding.
So Hubble announced that the universe was expanding,
and used data that looked like this, which to my mind is, it was an amazing result. It looks a little bit noisy today, and of course this print of it looks even noisier. But it's good enough to see this effect, that the ones that are here at the top of the graph, which are faster moving away from us, are in fact also the ones that are further.
so the further an object is away from us, the faster it is moving away from us. And so Hubble realized immediately that that meant the universe was expanding, but that may not be obvious to everyone in the audience. So thanks to the wonders of PowerPoint, I'm going to construct a toy model of the universe, and I'm going to expand it. So I've expanded the universe. It's great being able to do that. And if I choose a reference point, you can see what happens when you expand the universe. The objects that are nearby move a little bit when I expand the universe. The objects a long ways away move a lot. So the further away an object is, the faster it's moving. and you can see that's true in all directions. Furthermore, I can overlay this plot on a different side, and you see exactly the same thing. So it solved two problems. It explained the observations, but it got rid of that idea of us being in a special place in the universe. Everyone in the universe sees exactly the same thing. Now, imagine you take this and we extrapolate. Astronomers love to extrapolate. At least that's what theorists always accuse us of doing. And so we go through and we can expand the universe, or we can run it in reverse. And if you run it in reverse, you naturally get to a time when everything in the universe is on top of itself. And that is the thing we refer to now as the Big Bang.
Now, there's another whole way of looking at the redshift of those spectral lines, which really is what Einstein's theory of relativity leads us to model it as. So let me switch to an even cruder picture of the universe. Now you're supposed to imagine that these are galaxies spread out over space. And what you find is that if light leaves a distant galaxy over here and starts traveling to us in a universe that's expanding, the wavelength of light is getting stretched just as the expansion of the universe occurs, until by the time we actually see the light, it's been stretched to the point where it looks red, and how red it looks is telling you exactly how much the universe has stretched. So this is actually what we now think of as the source of that redshift that Hubble and Slipper were looking at. Now, you can now work your way backwards, and you can say, well, okay, so if I know, where I am today in the separation, average separation between galaxies as a function, and you know how fast that separation has been happening as a function of time, I can work backwards to the point at which everything was on top of each other, that Brian described as the Big Bang, and you can ask, well, what time was this? Because now you know what the age of the universe is, if it is working in this simple form.
So how fast the universe is expanding now tells us how old the universe is. It's just that ability to extrapolate back to the time of the Big Bang. Now, many of us in this room have worked on this project, and we have astronomers' units, which we call the Hubble constant, and I'm not going to go into that, but we think the Hubble constant in astronomers' units is 70, but that, in units that you will understand, means the universe is about 14 billion years old. So how fast the universe is expanding tells us how old the universe is, but here we have assumed something. We've assumed that the universe isn't slowing down or speeding up back in time. Now, we know the universe is full of gravity. We're all evidence of that in this room. At least there's some gravity in the universe. And gravity pulls on the universe and slows down the universal expansion as it expands. And so we have to worry about that in our calculations. So looking at that graph that Saul showed you, you can imagine that you have a universe slowing down with nothing in it, or going and not slowing down. It has nothing in it. It's just coasting. But imagine a universe that's full of material. Then it's going to do a different trajectory like this, where it's actually expanding faster in the past, slowing down in time. This is a universe which has a different trajectory, and so the Big Bang happened not as long as we thought. In this case, it would be about 9 billion years in the past. And so it is fundamental to understand the slowing down and speeding up of the universe to understand our universe. Of course, we can use this to extrapolate into the future. Because if I go through and do my same graph, imagine I have a universe which is coasting. It gets bigger and bigger and bigger the longer time is. This is a universe which is infinite. It goes on forever. If you have a universe instead on this trajectory, it starts off, and where we have the Big Bang here, you end up with the Gnab-Gib. That's the Big Bang backwards happens. That is a Bob Kirshner joke, my thesis supervisor. It always works. Thank you, Bob. All right. So, Saul is now going to tell you the other aspects of how this feeds in to the universe.
All right, so now from this information that we're describing, the slowing or possibly speeding up of the expansion of the universe is telling us, of course, how old we think the universe is in this way that you just heard. It's telling us the ultimate fate of the universe in the way that you just heard described. I still have a hard time pronouncing that. But it also tells you something even more, something to me even more bizarre, which is something about the shape and weight of the universe. Now, everything we've been describing is somewhat mind-boggling. I think even just the idea of infinite space itself already boggles the mind just to begin with. Now you have to imagine something that we learned in Einstein's theory of general relativity, which is that you can picture a universe in which space itself, three-dimensional space itself, curves. And it can curve in interesting ways. I mean, it can curve enough, in fact, so that it's that one, okay, curved enough so that in fact it closes in on itself. This is very bizarre. You travel as far as you want in any direction and you find yourself right back where you were before. It takes a long time, but you're back again. And that's a finite universe. There's not an infinite amount of space out there in that version of the universe. So that would be pretty amazing if we were able to go out and measure with the supernova, find out whether or not that's what we have. Now, the alternative is maybe even more bizarre, that there's, and by the way, what is it that's curving it? It's the actual stuff in space itself. So all the energy and mass in the universe actually acts on space and curves it in. So if you have a lot of stuff in the universe, if you weigh a heavy universe, you end up in a finite universe. Now the alternative is perhaps even more bizarre. This is a universe that has too little stuff in it, and the stuff curves out. So you actually have more space out there than you might have imagined. Let's go for the third alternative, which is Goldilocks just right. There you live in the old comfortable universe that you always imagined you lived in, that you go as far as you want in any direction, you're just where you are. You know, and that's the in-between point that the answer could turn out to be.
And I should say it's also the just right universe, because theorists, when I was a student, always told us that's the way the universe must be. And so it was always good to go out and see if they were correct.
We look at our resident theorists.
Yes, I am. But I can look in other ways. All right. So imagine an experiment. A simple-minded person like me would like to go through and measure the universe's past. So construct an experiment where we measure how fast the universe is expanding now and into the past. Now we have a great thing on our side, which is time, because the speed of light is not infinite. It's 300,000 kilometers per second. It takes light a long time to reach us from the other side of the universe. And so when we look at an object which is, for example, 4 billion light years away, its light is taking 4 billion years to reach us. And so imagine we can do the experiment where with nearby objects we do what Hubble did. We measure how fast the universe is expanding. And then we compare it to distant objects on the other side of the universe, 4, 5, 8 billion years into the past. If the universe is coasting, then the expansion rate will be the same. On the other hand, if the universe is slowing down rapidly because it's full of material, you can have a trajectory like this one, where on one side of the line, gravity wins. If we measure that, the universe ends in its Ganab give. Or gravity loses and the universe is infinite and lasts forever on the other side. A fundamental way at getting at this fundamental problem. So, and I should also say, you could also have, which from our punchline, the accelerating universe, where things would be expanding faster now and slower in the past, which would be quite remarkable indeed, as you will find out.
Okay, so the fate of the universe apparently then can be determined from its history. So here we are today, we look back here into the past, and we can determine the fate if we can see how much it was slowing down back here without determining whether it goes on forever or it turns over and collapses again in the future. So that's sort of the simple cartoon picture of what it is that we want to do. Now, it turned out that by the 1930s, Badet and Zwicky have a possible measurement tool, supernova, available. These are supernova are exploding stars, and just to show what one looks like, here's a distant galaxy, and this is a dramatic supernova explosion in that galaxy.
All right, so a type 1a supernova. What is a type 1a supernova? Well, to understand that, I think we have to understand the basics of what a star like our sun does. Our sun is going to, at about 10 billion years of age, 5 billion years from now, consume the Earth as a red giant, and then collapse down into a tiny little star called a white dwarf, which is about the size of the Earth, but the mass of the sun. So on this star, a teaspoon of material weighs a ton. They're a remarkable place. Now, that's not particularly relevant to a type 1a supernova. It gives you the idea of what a white dwarf is. Because imagine that you have the sun having a friend in a binary. Well, in this case, the first star will get big, and typically in this type of scenario, the other star does not get, and it's big enough, but the first star will become a white dwarf, and then the second star will start spilling material onto that star, growing it in mass under certain circumstances. And so, if a star, turns out from Chandrasekhar, reaches 1.4 times the mass of the sun, the star ends up exploding. Yeah. Saul, you're in charge.
All right, so these are dramatic explosions. This is an explosion 5 billion times brighter than the sun, and its expansion is about 10% of the speed of light. So you're really looking at quite an event. It lasts for just a little while, though. It takes about on the order of 20 days to reach its peak, and then it fades away in just a matter of months. And the let me see where we're going to from here, right? And you can we knew that this was a possible route to make this measurement even back in 1938, because there's a paper by Bada in which he actually proposes using the supernova for exactly this kind of measurement. Now, the only problem was, at that time, the supernova were not quite good enough standard candles. So the range of supernova explosions that he saw was fairly big. They really did not all boil down to one brightness, which would allow you to make this distance measurement that you want to make. And so the first, the big step that happened in this area that made a big difference in the 1980s was the idea that you could get a more standard candle if you could identify the subtype, the type 1A subtype. And a series of papers that came out, one backed by Kirshner here, in which the recognition that you actually were able to pull apart the subtype became important. Oh, wait. And for example, in the paper by Nino Panagia, he was able to show this distribution of the brightnesses of these supernovae, and identified that there was a group that was found in the older elliptical galaxy populations, where they all pretty much lined up at the same brightness, unlike the more general range of supernovae that were seen. So this meant that you were beginning to have the possibility of going out and making that measurement that Bada had suggested back in the late 30s. Of course, the quality of this particular data set that we had available back then to do this was not what you would like for this job. And I think what's dramatic, the next step, that was a really dramatic step, was the Kalan-Tololo supernova search. And this is a search for supernovae that were nearby, but they studied with a level of precision that hadn't been done before. It was led by Chileans, Mario Mui and Jose Maza, and a group who are all represented here, Nick Sunset, Bob Schomer, Mark Phillips, and Chris Smith. And what did they see?
Well, so this group was able to go out and find 29 type 1A supernovae and get digital data on them, which was of very high quality. This is the first time. And so this data set provided the fundamental basis of using type 1A supernova as accurate distance indicators. And their data set was used by both teams as sort of one end of the lever arm to measure the acceleration. Because when you measure acceleration, you have to compare nearby to far. And so their techniques ended up allowing you to measure distances with a precision of about 7%, which by astronomical terms is extraordinary. And so one of the things they had to use was a trick that Mark Phillips, represented here in the audience, developed in 1993, where he realized that how fast a supernova fades is related to its intrinsic brightness, how many watts the object is. And so in the schematic diagram, objects which fall quickly are not as bright as objects which fall slowly. Now his was not the only way which was attacked, but his was really the first.
So what did this Kalan-Tololo supernova data look like when you try to plot it up? Well, so here's a plot that actually I think maybe that was Kim, or Kim was working with, and you can see that if you plot these, each of these lines represents a different supernova, with the dots representing the data for that supernova, and they do span a fairly wide range of brightnesses. So this is brightness, of course, this direction. Some rise slower and fade slower, and those are the brighter ones. Some rise quicker and fade quicker, but conveniently it means the number of lines overlap when you try and plot them all together. But it means that you can use these various techniques. You heard about the decline rate, which was used by Mark Phillips. We used the stretch of the time axis as our measure of which were the slower and which were the faster supernova. And if you take that stretch and you then calibrate the brightness of every supernova using that stretch, this big range of supernova all turns into this beautifully tight calibration group shown here.
All right. Well, we were different teams, so we also had other techniques. One invented by Adam Reese as part of his thesis with Bob Kirshner and Bill Press at Harvard, just to show you how well this type of relationship worked. In their paper, they were able to take this normal, uncorrected for Mark Phillips's idea, sample to get distances from 20% accuracy to 7%. Now it turns out that level of improvement makes life 9 times easier, which is a huge difference. So all of the methods have a similar improvement, but this was a technique that we used in addition to the one that Mark Phillips did, where Saul used stretch.
So this was some of the major steps forward in this understanding of the supernova that made everything you'll be hearing about possible. There was also, in the mid-'80s, some technological developments that made a very big difference. And those include the invention and the development of and the use of these CCD detectors, which by now everybody's familiar with in the back of every one of these digital cameras you see in your room, you probably have in your pocket or your phone. And they, at that time, they were brand new for this kind of work. And also, computers are fast enough to do the analysis of the huge amounts of data that you produce when you take an image with a CCD camera. We've been working at Berkeley using one of the very first of these CCD cameras that we could get our hands on to do a relatively nearby supernova search. And there what you can do is you can get a picture of a supernova and a galaxy, and you subtract one from the other, and you get supernova. So this was our Carl Pennypacker and I were working with Rich Muller's group on this at the time. And so you started turning out a few dozen of these supernovas, so we were familiar with this kind of image analysis technique. So that was all great. We had a technique, we had a tool, we had supernova, but in fact, at the end of the day, supernova are not the kind of research tool that you'd like to use. If you find anything else, you would, because they're really a pain in the neck. They're rare, they only explode a couple times per millennium, the type 1A that we're trying to find. And they're random. You can't schedule the telescope time in advance, because you don't know when that next 500 years will happen in any given galaxy. And they're really difficult to catch on the rise because, as I mentioned, they're rising in just a few weeks and they're fading in just a few months. So there had been a concerted effort that was done by a Danish team, a rather small team with some Danes and Richard Ellis and Mark Couch, who's here in our team, which for several years searched intensively for these very, very distant type 1A supernova, and at the end of several years, they had found one, what looked like a type 1A, and that was a heroic effort, but even that one supernova was found several weeks past that peak that you want to use to calibrate the brightness. So we at least knew they existed from this work, but they were going to be really difficult people doubted that you could actually do a project based on the possibility of, after several years, possibly finding one and having it be already past its calibratable peak. So we ended up trying to find a new way to work on this. Carl Pennypacker, working with me at Berkeley, and Carl suggested that the idea of a novel wide field camera, and then went to Australia and found the novel pioneering effort that was willing to go along with that camera to put it on a big 4-meter telescope. And this allowed you to look through hundreds of galaxies in every image, and with a big enough field, you could then collect enough galaxies to find enough supernovae. Now, this is what that looked like from that very first camera, a very first wide field camera of this kind. And so in 1988, you saw a field that looked like this. All these little smudges here are distant galaxies in which you want to find a supernova. If you take an image some months or so later and reverse it, it looks like this. And then if you subtract one from the other digitally with that telescope, you end up seeing a supernova, which of course is a dramatic, bright thing that's thousands, hugely brighter than the sun, and this is the thing that we have to find in that field. So it was a bit of a tough job to pull these little specks of light out from these big fields, and you had to look through hundreds of them. And to make matters worse, the timing was still not a solid problem. You found them still at a random moment, and that wasn't good enough to be able to then follow the supernova and recognize it spectroscopically. So we ended up developing a search strategy to get around this timing problem. And the idea was that you always want to be able to find the supernova right before the new moon, because you want to be able to follow it using the largest telescopes in the world. And these, on a bright night, you can't observe such faint objects. So this is how you lined up the approach. you did the search was a bunch of images you collected just after new moon, and then you collected the same images again just before the next new moon. You did the subtraction of the two and found the spot that got right, and then you can now schedule all the follow-up right after the next new moon. So that really was the step forward that made it possible to now guarantee that you would have supernova on a certain night, so you could schedule all the follow-up points along the light curve, follow-up photometry, and the follow-up spectroscopy. So that really, for us, made a very big difference to be able to move into this next step.
So, finding these objects, Saul makes sound very easy, but it is anything but. Here is 1/8 of one picture we might take. And there's approximately 5,000 galaxies in this picture. And so the key is to find the supernova. Can you see it? Well, I'll show you where it's at. It's right there. You always tell a supernova it's a little star next to a galaxy. Unfortunately, there's lots of stars next to galaxies. And so the process of finding these is quite dramatic. As Saul said, you use the computer to do this. But this is not as easy as it sounds. And so I thought it would be useful to show you sort of a movie of how this all works as best I can. And so we'll see how this works. So Sarah Chilowo is where we both started out looking at things. And here's CGIO at a night. And we have Greg here looking out at the sun. Is Greg Aldering from Saul's team. Nick Sunseth on a different night going through and getting ready to start observing. And we watch the stars go by as the night goes on. Now you might think we're out sipping Chardonnay at this point, but anything but. We're in the this is Bob Schomer here running the telescope, and we have our sweatshop here looking for supernovae, in our case in Chile, in Saul's case in Berkeley. Meanwhile, on the other side of the world, in Hawaii, we're using the largest telescopes to really make sure what we find are type 1a supernovas. So here's the Keck telescope, still the world's largest telescope, and we have Alex and Adam running the telescope, trying to figure out what they're looking at, and Saul's team, of course, doing exactly the same thing. We ended up using almost exactly the same facilities. And that is more or less how we found it, but I should say there was a lot of blood, sweat, and tears there.
So at the end of the day, you end up with these telegrams. These are the International Astronomical Union telegrams that start appearing every semester. So you churn out a batch of perhaps a dozen supernova semester after semester at these telescopes, until finally, after a few years of this, we reached 1997, the possibility of going back to this plot again. And now, instead of these nearby supernovae that are plotted as these little black dots over here in recent time, right before today, we're going back here to the past to try to tell which of these lines we live on. So we're going to start putting black dots on these lines to distinguish, are we on the curve that is curving more and more back here, so there's more deceleration, implying that it will curve in the future and turn over and into a nav gib. Or are we on a universe that's a lightweight, which will just expand forever, always decelerating. And of course, the result that we found from both teams was
a big surprise.
So this is the none of the above scenario, and that's well above, I guess. And that's what we found. And apparently, this is not the full range of lines that we have to look at. We are apparently living on a universe that was slowing in the past, it's curving this way as in that early plot that Brian showed you, but is now apparently accelerating, going up that way.
So showing this in my version of a diagram, if we go through and look at this in terms of the expansion rate back in time, the objects in the nearby universe go through and tell us the expansion rate now. And then when we look back in time, we see the universe was expanding slower in the past and has sped up. And so it's quite a remarkable thing. And these results are in our respective papers here by Adam Rees et al., who of knowledge wrote our paper and did a lot of the work on it, and Saul's paper, which both appeared now almost 10 years ago. So we have an accelerating universe. The type 1a supernova measurements indicate a universe which is a 30-70% mix of material which can pull on the universe, 30%, and universe which is stuff that's been pushing on the universe, 70%. And so this is a funny mix that our final analysis of our data, I guess, indicated. But you don't just have to believe us, because needless to say, in 1998, this did get some attention, and other people decided they better check out what's going on. And it is for that reason, I think, that people have become truly convinced of this measurement. And so one of the first things that was done was by other people in the room, not represented by the team, called the AAT 2DF redshift survey, and a similar Sloan redshift survey, which went out and did a cosmic census. They essentially measured how all the galaxies in the nearby universe and ended up weighing the universe in this census and seeing how much stuff in the universe that has gravity, that stuff that could pull on the universe. And when they did that, they found that about 27% of the universe the universe was composed of about 28% of the amount of stuff necessary to make it flat. That is, the stuff that could tug on the universe was only 28%. It was not 100%.
Now, there's another route that you can make towards accounting for all of the entities in the universe, not only the stuff that pulls on the universe, but also all the other energies, including those that might push out. And that's look back at that glow left over from the Big Bang called the cosmic microwave background. Now this glow has these sort of hotter and colder spots on it, and data just after within a year or so after the 1998 announcements, was coming in fast and furious from two balloon experiments, Boomerang and Maxima, and then more recently, you may have seen this version of it from the satellite, WMAP satellite. Now the scales of the distances between these hot and cold spots on the sky actually gives you a counting of the full effect of all the stuff in the universe. So if you get points, sorry, okay. So if these spots are far apart, then that actually is a representation of a universe which is closed in that bizarre way where you can travel as far as you want in any direction, you end up somewhere back where you were before. If you end up in a universe with the spots very close together, that's curved out in the open, where it's describing, and then of course the just right Goldilocks phenomenon of the flat universe turned out to be actually what they found. So it turns out that within 2%, they were making measurements that implied that the universe is just the garden variety universe that you always knew and loved, that you walk around it, you end up going further away, you don't come back where you started from. So this is what we learned just within a year and a half after we presented these results.
All right, so now I'm going to do something which is not rocket science. It's called subtraction, and I think most people will be able to follow this. The cosmic microwave background experiment measures everything that's in the universe, whether or not it pushes or pulls. And they found 102% out of the compared to the matter to make the universe flat. On the other hand, the redshift service, the AAT and Sloan experiments, go out and they measure the stuff that can pull on the universe only. And so there's a difference between those two. You have 102%, you have 27%, and the difference between these things is 75%, which is this mystery matter. And we think now today that mystery matter, which is the difference between these two experiments, is the same stuff the supernovae are seeing accelerating the universe. And so together, we have a very interesting situation.
So we end up with this rather messy story that we have to tell, because what we know about, what we don't know about is this mystery matter is something that is just the part that you need to explain this acceleration. We're using the term dark energy. And energy because it's one way of getting things to accelerate. Dark because we're in the dark. We don't know what it is. And most of the universe apparently is made out of this stuff. Now, the remaining part of the universe is not exactly well known either. We still have this dark matter, which for many years many of you will have heard about, where we don't know what that stuff is that does gravitationally attract, and it's still a mystery in and of itself. The things that we know about is this paltry 4%, and that's what we're made of, and the things that we're used to studying. So we've got a lot of work to do ahead of us if we're going to start understanding this full universe, including the dark matter and the dark energy. Now, if you ask what kinds of things could this dark energy be, Well, it turns out that if you go back to the earliest papers by Einstein in his theories of general relativity, when he tried to explain the universe that you could predict from his theory, he introduced a rather interesting fudge factor, the cosmological constant, in his equations, because he couldn't figure out a way to get a universe that wouldn't expand or contract, that would just stand still. And as far as he knew at the time, we lived in a universe that stands still. He couldn't imagine a universe that was expanding or contracting. And he added this extra term, which was sort of designed to just counteract gravity and kind of make it balance. It turns out that, in fact, it doesn't really work very well at all, and he was actually rather glad when he could remove it from his story. He called it his greatest blunder in retrospect. And so once Hubble saw the expansion, he realized he didn't need it anymore because he could actually let the universe expand in his theories. Now, today, we realize that you can get that same cosmological constant by just looking at what quantum mechanics would have predicted for this, what's going on in empty space, in the vacuum. Now, many of you may have heard that empty space in quantum mechanics is a constant humming, bubbling cauldron of virtual particles appearing and disappearing, and that hum, that buzz, actually has energy associated with it, and in fact, that would act like this dark energy that we're describing. It would act to expand the universe faster. It has other problems with it as well, but in principle, that could be what we're looking at, Einstein's cosmological constant.
So, Einstein's cosmological constant is tied to space itself. And so we have this interesting situation that the more space expands, the more cosmological constant we have. So dark energy, over time as the universe expands, becomes a stronger and stronger force, ripping apart the universe. Dark matter, or gravitating matter, on the other hand, gets diluted by the expansion of the universe. And so we expect dark energy, if there is any, eventually to sort of win the battle of the cosmos in most situations. But it also means that if we go back in time, we should be able to look back to a time when the universe was actually dominated by dark matter. And so the universe should be slowing down in the past, and it's only recently that it has sped up. And so, to give you an idea, you can imagine a little movie like this, where gravity is slowing down the universe at the beginning, and then at some point it gets big enough where dark energy ends up overwhelming the rest of the universe and speeding it up and ripping it apart into time. Now, that means if you look back far enough in time, you should be able to test this. And people have done this in this room, been able to look back this far in time with the Hubble Space Telescope. So just to show you how far they look, NASA's produced this lovely movie where we zoom in to a part of space which contains the most distant object, supernova, ever detected by humankind. And this object is almost 11 billion years into the past. My favorite part of this animation is the really cheesy NASA thing at the end, right there. That is our exploding star. But it is still a remarkable discovery. So this object was discovered by a team made up of people on both sides. Oops, thank you. Go back. Led by Ron Gilliland. And then, in a series of papers, Adam Rees analyzed this object, and with other people also again on both teams. And then in a series of papers, he's actually gone out and found literally 50 of these objects, and they see exactly what is predicted. The universe has only recently started speeding up. And so it seems to be exactly what you might expect. So, oh, sorry, this is my turn still. So the goal of the future is to understand dark energy. The big question for physics right now is, does it get created exactly with the creation of space? Or is it a little bit slower, a little bit faster? This has been labeled in the US as one of physics' biggest questions, and it certainly has captured the minds of the US, Europe, Japan, and Australia, for example, but other places. Now, it is kind of entertaining to me that this is causing some sociological problems, because this is big, big science, which is not what astronomers are used to doing. And so people have asked, including one of the people who gave this prize, decided on it, Simon White, is dark energy bad for astronomy? And I think we're still trying to come to grapple with that. It certainly has its good sides, as I think it's a great discovery. But it is an interesting problem of how to solve it. And so, what are the consequences of this?
So you can end up with various future scenarios coming out of the various possible explanations for what dark energy is. So in some of the simplest versions, you end up with what we call the big chill scenario. You have basically a universe is expanding, and as that space gets created to make the expanding universe, dark energy gets created exactly with it. And so dark energy, in the end, wins the battle over the universe, and will just continue to accelerate the cosmos. And as space just gets created more and more quickly, as time goes on, eventually we live in an empty universe, except for perhaps our super galaxy. So I've been saying to people who are interested in getting into astronomy, they should start doing it soon. Just mathematically, just billions of years, and you'll be out of a job. But we do have a chance still to do some work. Now, it turns out we do not know at all what this dark energy is. It may be something more bizarre than the cosmological constant, which is bizarre in and of itself. And there's lots of alternatives. So one example of such an alternative is called the Big Rip version. And there, actually, you get dark energy created even faster than the space itself gets created. And so you end up with something like a runaway situation where everything gets pushed apart, even at the atomic level, leaving essentially nothing. It's a slightly more depressing scenario. I'm not sure.
No, I think that's exciting. Anyway, so people are working on this around the globe, and there are a variety of projects which include people from both teams intermixing now fairly freely. But interestingly enough, the more and harder we look, the more and more this dark energy looks just like Einstein's cosmological constant. But unfortunately, we're not yet anywhere near enough to really please the people who are working on the theories of trying to understand this dark energy. And so this is something Saul is putting a lot of effort in, as are other people in this group.
So just to get at the level that distinguishes theories of dark energy, you need a much more delicate measurement. And you actually need to use more than just the supernova technique. If those who want to stay for another few hours can describe the other two techniques that are on the table. But you should know that now there are a few other techniques that have just now been developed for this problem. So to get the level of precision that we think we're going to need, we ended up proposing the idea of doing a space mission. And so this was this idea of this project called SNAP, Supernova Acceleration Probe. But both Department of Energy in the United States, which does fundamental physics problems, and NASA both became interested in working on this problem. And so they decided to do it jointly together, a joint dark energy mission. And so now it was reopened up for competition, and basically in the room there are members of all three of the possible competing teams to work on this project: SNAP, Destiny, and DEP. And I think all three of these teams were very happy the night before last, 2 nights ago, when the National Academy of Sciences in the United States came out with their recommendation to essentially to NASA as to if NASA is now ready to go ahead with its what they call Beyond Einstein project. This is the science that they do when they're not going to the moon and Mars. But if they're ready to go ahead with the next one, that the one that they should start with is in fact one of these JDAM missions. So we're all now feeling excited because there's the possibility that we're going to get to do this next step forward, and we'll get to do it finally in the not so distant future.
So, in closing, I think the thing that we've learned here today is that's how the universe ends, not with a gnab, but a whimper, where we expand out to infinity.
Or just possibly with a screen.
Thank you very much.
I think members of the audience may have 1 or 2 questions for you. So,
Be careful how you ask the question because we have to answer it in unison. Yes, no questions,
You said one of the fates might be that we end up in one super galaxy. Why super galaxy? Is it just to be a regular galaxy?
Well, it will be a very large galaxy because it turns out that there are parts of the universe where the gravity of galaxies near us have already won our little battle in our part of the universe. So the universe, for example, between us and the nearest galaxy, the Andromeda spiral, which you can see up in the sky at night, is actually collapsing. And so dark energy is never going to get a toehold in there. And so over the billions of years between now and in the future, all those galaxies which are the universe is currently collapsing or going to collapse are going to join into one big super galaxy. And so we're going to be living in a bigger galaxy in the future. But everything else where gravity can't get in there and stop the expansion is lost. That ends up getting pushed away forever.
Virginia?
What questions couldn't you answer in unison because you disagree?
It's a good question. Is there anything now that we would, I mean, trouble is we know so little about what dark energy will turn out to be that it's hard to have really strong positions on them to disagree about.
Yeah, I think there are certainly interpretations of history where there's disagreement. That's one. We may disagree on whether or not dark energy is good or bad for astronomy. But I think on the science, as you say, we know so little that we actually agree pretty much on the science now.
Somebody actually, at the time of even 1998, when we were in our tightest rivalry, at that time, somebody after one of the talks said, "They understand why were you guys sounding so so argumentative? It sounds like you're in violent agreement."
You mentioned you finished by the lecture by mentioning the joint missions for the future. I was just wondering, Saul implied that it's not only type 1a supernovas, you can use as standard candles. What would these missions be looking at?
Right now, I'd say the leading contenders for the ones you want to use together at this stage, and we hope that there'll be other ones developed, but the three that look the strongest at the moment are the supernova. There's a technique called gravitational weak lensing. So this is where you're looking at the distortion of the shapes of very, very distant galaxies by the intervening matter between us and them, and they slightly elongate in the shape of these distant galaxies. Very subtle statistical effect. So it's, you have to average millions of these things together. So therefore, you have to do it very precisely, or else you average together stuff and you get something that's meaningless. That's technique number 2. Technique number 3 is slightly more recent, called baryon acoustic oscillations. And the idea there is that that same pattern that I showed you of the hot and cold spots on the Big Bang, on the cosmic microwave background, that glow left over from the Big Bang, those set a scale in the universe that we actually can precisely calculate how big those distances are. And then you can watch them evolve to where there are overdensities of distances between galaxies today. And that allows you another route at measuring this expansion history of the universe. The three together are actually very complementary because among the possible explanations for this acceleration, it doesn't have to be a new energy in the universe. It's possible, for example, that Einstein's theory of general relativity needs to be modified, that it's not quite complete with or without his cosmological constant. And so that is something that you can only tell apart if you have different techniques that are affected differently by gravity versus, let's say, the expansion of the universe, and in particular the weak lensing with the others gives us that.
Questions? There's one there.
So far, I mean, it seems that we are going towards a universe in which this dark energy is sort of the cosmological constant. And in that case, I think the experiment to do is something like the one that has been done already, measuring the homogeneous properties of this dark energy. But if it is not, it might have condensation properties. And in that case, there could be some other different experiment to test that. Do you have anything in mind regarding that possibility?
So the idea here, just to translate, is that dark energy might be not directly tied to space, but have little bits extra in one piece of space, a little bit under in other pieces of space. And that's going to affect the experiments we try to do slightly differently, depending on exactly how dark energy is created. And so it does end up, I think, in some of the experiments, especially, again, the weak lensing, where you can actually see where mass is in the universe and see how it affects things, it could affect those more than others. But it is very difficult, as you know, to do that type of stuff.
Questions?
Slightly different direction. In terms of your work, this is getting to be increasingly expensive. So, the next project, $1 billion or so. Is astronomy a science, though, that very small budget and still there are still big discoveries to be made without spending $1 billion?
No, I think it's, and here's one we'll later refer to Simon White's paper essay later, but I think there's still a lot of room at all levels. There are questions that you want to answer that are, at many different hierarchies of size of project. And I think just the fact that you are getting a question that seems big enough that you're willing to spend a space mission budget on doesn't mean that you're not finding other questions that are fascinating that you can answer, for hundreds of thousands of dollars or less.
So I think the important thing is the only way we know how to attack dark energy, that is, see why the universe is accelerating, is big budget stuff. Now that does not mean that some clever person isn't going to figure out how to solve it with $2,000, but we don't know that. We do know how to get at it with lots of money, but we can hope that some random act of some brilliance will solve it cheaply. But I think we need to take both approaches. There's wisdom letting both goes go.
Thank you. Right, well, thank you very much again for that fantastic lecture. And, we have tea and coffee outside for all of you to refresh yourselves before going home to ponder on all this, figure out how to do something with $2,000.
A joint photograph of all the team members together in this room before just before we exit. So if people come, we do it. Yeah, right here. Okay.
Go this way.
Yes.
A couple of those. And again.
Let's see, big rip.
And again. Here we go. Oops.
The back up.
We will send the digital photos to everyone.
Neil, wait just a second, let's kill the bottle.
And smile. Thank you, Mary, out of shot. That would be nice.
Thank you.
And we'll do that again. Saul's camera's gone to sleep. There we go. Thank you very much.
Yeah, well, sure, honey.